So these are the day 49 solutions. So the first problem starts with an interest rate problem where we're told that after 236 days, we record a 44.3% return on our investment, and we want to know what the annual rate of growth is. So what we want to do is start with our interest rate formula, which is this. And it's really important to know what your rate is and what your time are. So I want my rate to be an annual, which means whatever I put up here has to be in years. So if I were to rewrite this, I would maybe write something like this. I'll worry about A and P in a second, but here I want, this is my R yearly. And up here, since my inputs are going to be days and I want it to end up being years, I'm probably going to put I'll put D over 365. So now after however many days there are, it'll convert it to years and give me a yearly rate. The last thing we have to figure out is how to, we need one variable. So I know I can plug 236 in for D, but I need to find out how to consolidate A and P. And the way we're going to do that is if you just let A be 1.443P, that means that after that day on the 63rd, we know that that's going to be the ratio of A to P. Sometimes you can write this like this. Is actually a better way to write it. So now we can sub everything together, and I'm going to get 1.443P is going to be P1 plus R yearly to the 236 over 365. And so it's nice, the P's cancel. And then as we go back through this algebraically, we're going to get that 1.443, and we've got to raise that to the 365 over 236 is going to be 1 plus RY. And if you go through and calculate that, you get R annual is going to be equal to 76.33%. So for problem 2, we've got an ellipse that they give us, and the first thing we're going to want to do is put it into standard form, and then we have to do some distance calculations to confirm eccentricity and distances like we've done in the past. So I do have it graphed here over on the side, but just to show you where that graph comes from, here's how we do that. So we're just going to divide everything by 3600. And that gives us x squared over 225 plus y squared over 144 equals 1. And now, since I know A and B, I know that the distance from here to here must be my minor axis. So that's going to be the B, so that's going to be 12. So that tells me that this point right here is going to be 0, 12. And I'm going to pick that to be the point to verify because I know that they tell us that the focus is here, and that's at 9, 0. So I really just need to check this distance and this distance. I'll call it D1 and D2 and verify that it matches the eccentricity. So D1, you can do a quick calculation there, but it makes a 3, 4, 5 triangle. So D1 is actually just 15, and then D2 we can see is just 25 minus 0, which is 25. So if we look at a ratio of D1 to D2, we get 15 to 25, which is divide both sides by 5, and you get 3 to 5. So for problem 3, all we're doing is looking and finding another directrix and another focus, and it's pretty easy to see by symmetry that the other focus, we know C is 9, so the other focus is going to be over here, and then there should be another directrix over this way. And if you just use symmetry, you'll find out, well, we can use C to calculate this. So this is that point G, and then the other, it's not quite on this graph, but then the other directrix will be out here, and that will be at x equals negative 25. And then another part of this question, I'll put f back, is just if you pick any point P, what is the sum of the distances from P to G and P to F? So there's, P to G and P to F right there. And we can see that's our string. So we know immediately that PF plus PG needs to be our string length, which, if you recall, is 2a. And if you look up above, our a was the square root of 225, which was 15. So that's going to be 2 times 15, which is 30. So that's the sum of the distance from any point to the two foci on this ellipse. Okay, so problem 3 is a tessellation problem, and we're trying to find the ratio of the area of these pennies to the hexagon. And the reason I chose this hexagon is because it was a convenient geometric shape to fit around a set number of pennies that I knew. And I know how to find the area of the hexagon once I find the area of the pennies. But it turns out that finding the area of this hexagon is pretty challenging. So what we're going to do is we're going to find the area of a slightly different hexagon. So what I'm going to do is connect the centers of the surrounding pennies and create an inner hexagon. So here that is. I zoomed in a little bit so we could see it better. And so now if I look at this hexagon, I can see that it's going to connect the centers. So each side of the hexagon is going to be twice whatever the radius is. And since we aren't given anything in this problem, let's just call the radius r. So then I could call each of these radii r. So I've got sides of r all the way around. And then what I'm going to do, because I'm going to need to find the area of this hexagon, I'm going to create a triangle here. Since it's a hexagon, I know that that's going to be equilateral, and then we can drop a hypotenuse and make it 30, 60, 90. So what I'm going to do is draw that over here. So here's my lopsided 30, 60, 90 triangle. So if this is r and this is r root 3, and this is 2r, which matches our situation, because we can see over here on this side we have an r here and an r here, so that's perfect. So what I'm going to do then is find the area of the hexagon based off of one of these triangles. So the area of the hexagon is going to be 6, because I've got 6 of those triangles all the way around. 1/2, the base is going to be 2r, the height is going to be r root 3. So that's the area of the hexagonal base. So that's going to be, so the 2 and the 1/2 are going to cancel. So I'm going to get 6r squared times root 3 for the area of the hexagons. And then what we've got to do is look at how many circles are inside this hexagon. So I've clearly got one here. And then it turns out that if you remember century theorem, the interior angle here is 120 degrees. So that means each one of these are a third of a circle. So you have 1, 2, 3, 4, 5, 6 of them. So that makes 2 circles plus the one in the middle. So we actually have 3 circles. So the area of the circles is 3 pi r squared. And then finally we need to do the ratio of the area of the circles over the area of the hexagon, which is going to be 3 pi r squared over 6r squared root 3. Some things are going to cancel here. So we've got a 3 and the 6 is going to turn into 2. The r squareds cancel. And then we're down to just pi over 2 root 3, which is approximately 0.9069. And so if we turn that into a percentage, it's going to be, what, 90.7% approximately. And then we can see that if we tiled or did a tessellation of all of these, no matter how big my surface was, I could just keep breaking it into these hexagons, and so that ratio would always be the same. Problem 5 is just a simple exponential problem, so we start with our basic. They used k and b in this example, and all we're going to do is plug in the given points, which are 1, 6, and 324. So 1, 6, and 324. So first I'm going to plug in 1, 6, so that means that 6 is equal to k times b to the 1, and then 324 is going to look like 24 equals k times b to the 3. And what I'm going to do is simplify this first equation and solve for one variable and then substitute into the other. So what that's going to look like is, let's solve for k. So k is going to be equal to 6 over b. And then I'm going to sub that in, so I'll get 24 equals 6 over b times b cubed. So we're going to have some cancellation of the b's here. So 24 equals 6b squared, and then 4 equals b squared, which gives us b is equal to 2. Once you find b, you can find k. So I'm going to come back over here. So k is just 6 over b, which is 3. So my k is 3 and my b is 2 for that problem. Okay, for our last problem, we've got another ellipse. And what we're going to do is we're going to basically just show the same thing we've shown before. It's just kind of practice coming up with the equation given a directrix and a focus for an ellipse. So the most important thing on this problem is just pick some random point, call it P, and make sure its components are x, y. And then what we're going to do is we're going to write equations for P to F and then P to lambda. Make sure you pick the shortest distance. And then we're going to use what they give us for an eccentricity to create an equation. So I like to call this D1 and this D2. Well, I also think it's easy if you find this point, it can help you out a lot. So the x is obviously 5, and the y is going to be y. So finding that point just helps you with distance formula if you get confused. So our equation is going to be, according to what they give us, D1 is equal to 2/3 D2. So plugging in with distance formula and everything, we're going to get D1 is going to be x minus 0, y minus 0. 2/3, and then this distance, I'll just write it all the way out in distance formula, is just x minus 5 and y minus y. And so what we can do is simplify a little bit. So we're just going to have x squared plus y squared, square rooted on this side, and then we're going to have 2/3. And so the y's are going to cancel, and we'll just have the x minus 5 squared. And so now I'm going to square both sides and be careful to square everything. And then we can expand, and I'm going to multiply the 9 over to the other side. So that's going to give me 9x squared plus 9y squared equals 4 times, and I'll expand this, x squared minus 10x plus 25. Just scroll down a little bit here, and then I'm going to distribute the 4. And then we're going to rearrange 5x squared plus 40x plus 9y squared equals 100. So we'll factor out the 5 so we can complete the square. So that gives me an 8x. And then I'll complete the square. So 8 divided by 2 is 4, squared is 16. So I added 16 to that side, but I really added 16 times 5. So I really added an 80. So now I need to add 80 to this side. Oh, I need the equal sign. So there's my 80 to that side. So I just scrolled down a little bit. So now if we factor, we get 5x plus 4 quantity squared plus 9y squared is 180. And then to get into standard form of an ellipse, we divide everything by 180. So what we're going to get is an x plus 4 squared over 36, and a y squared over 20 is equal to 1. And that is going to be the standard form equation of our ellipse. And then they wanted us to check the eccentricity. So this is going to be a squared, this is b squared. And then I need to know, so eccentricity is c over a. I haven't found c yet, so let's find c. I'll do that down here. So c is the square root of a squared minus b squared. So that's just going to be the square root of 36 minus 20, which is equal to 4. So my eccentricity come back up now is going to be 4 over 36, 4 over 6, because 36 is a squared, and that's just going to be 2 over 3. So we can verify that the eccentricity does match the one they gave us to make the equation out of.